Exponential function. This video, we want to talk about exponential function, learn how we can evaluate them with different values, how we can graph them, and how we can use them to work on application problems. Exponential function means the function that x is on the exponent of something. For example, this is an exponential function because x is the exponent of 2, or 3 to the x power, or 3 to the x plus 1 minus 2. As long as x is an exponent of something, we call it exponential function. But before we start talking about exponential function, I want to just have a review about the properties of the exponent, because we need them when we are working with exponential function. First thing that we had about the properties of the exponent is that when you see two exponential expressions are multiplying together and the bases are the same, you can just keep the base the same and add the powers. What does it mean? It means I want to multiply 2 to the third power by 2 to the fifth power. Each of these are exponential terms. So in each exponential term, we have a base and we have exponent. When you want to multiply two of them and you see the bases are the same, you just keep the base the same and add the powers. And 3 plus 5 gives you 8. We also have this another property when we are dividing exponential function. When you are dividing two exponential function and the base again, the bases are the same, you just keep the base the same and subtract the powers. And you say 5 minus 4, which is 1. So the answer is 1. And that division can be written as a fraction, or it can be written with the division sign. So every time dividing two exponential term, when the bases are the same, you keep the base the same and subtract the powers. Every time you see an exponential term has one base that with the two powers, like I have 2 to the third power, which is also going to be raised to the fifth power. That means I have one base with two powers. Every time we have two powers, we need to keep the base and just multiply the powers. And 3 times 5 gives us 15. Why? Because exponent means multiply something by itself. When I say 2 to the third power, I mean multiply 2 by itself 3 times. Now, if I want to raise it to the fifth power, that means I want to multiply that 5 more times. I want to have these 3 2's 5 more times. So 1, twice, 3 times, 4 times, and 5 times. And you can see that we are multiplying 2 by itself 15 times. So that's why we just multiply the powers. Next property is talking about multiplication or division when bases are not the same, but the powers are the same. For example, this time you want to multiply two exponential terms. But this time, the bases are not the same, the powers are the same. Every time the powers are the same, which means you can keep the power and multiply the bases, and 2 times 4, which is 8. Or if you see that two terms are inside the parenthesis with the same power outside, That means that power is for everything that's inside the parenthesis. If you want to drop the parenthesis, you need to give each term a power of 2. And that worked for division as well. If you see two numbers or two terms are dividing with the power, that means this power is for everything inside the parenthesis, is for 2, it's for x, and it's for 3. If you can simplify inside the parenthesis, you can simplify first and then raise it to the power of 3. If not, you can raise each term with the power of 3 and then multiply or divide by each other. Next rule or next property is talking about negative exponent. What does a negative exponent mean? Because when we say that the exponent means multiply something by itself that many times. But what does the negative exponent mean? For example, if I have 2 to the negative third power, can I say I want to multiply 2 by itself negative 3 times? No, that doesn't make sense. So we cannot have a negative, we cannot keep the negative exponent. We always have to change it to the positive. And we can only change negative exponent to positive if we just move it, if it's on the top to the bottom, if it's at the bottom to the top. So right now, 2 is on the numerator of a fraction. If you want to change it to the power positive exponent, you need to move it to the denominator of exponent. Base and its power stay the same, only the negative exponent would change to a positive. So that's why you see here that every time you see a negative exponent, you just move it to denominator. If there is nothing left on top, just leave 1. If something is at the bottom, and you want to move it to the top, you know that you have to change the exponent to positive. Zero exponent. Zero exponent means multiply something by itself 0 times, which means actually doing nothing. So that's why every time we have a zero exponent, for every number, we just have 1. What is 2 to the 0 power? Is 1. 5 to the 0 power, 1. 6 to the 0 power, 1. X to the 0 power, 1. Anytime you see a 0 power 1, x squared, y cubed, z with the 0 power. I don't care what's inside. As long as I have a 0 power, the whole is equal to 1. Fraction. If I have exponent in fraction form, like I have 4 with the power of 1/2, the exponent is a fraction. What does it mean? That means we have a radical. Fraction in an exponent means a radical. If you see 4 with the 1/2 power, that means you have a radical 4. And always the top number is the power of the number and the bottom number is the root of the radical. So the power of 4 is 1, the root is 2. So it means we have a square root of 4. And I know that the square root of 4 is 2. If I have 5 with the 2/3 power, what does it mean? That means I have a radical 5. The power is 2, the root is 3. The power is 2, the root is 3. So when you see fraction as an exponent, that means that you have to change it to radical form. Or vice versa. Sometimes you need to change radical to exponent form to exponential form. And you would see it in this video or maybe the other videos for next sections. And the last property, which tells me that if I have, for example, 3 to the second power, and I want to raise it to the 1/2 power. So we said every time we have one base with 2 power, the powers must be multiplied together. And if you multiply 2 by 1/2, that means these 2 can cancel each other, so you just have 3. If they are that exactly reciprocal of each other, the number 2 and 1/2, 3 and 1/3, 4 and 1/4. So these are the properties of the exponent. We need to know them when we were working with the problem. Okay, now let's start talking about the exponential function. So exponential function, as I said, it's a function that the x is an exponent of something. And the general form of exponential function can be written in this form, a times b to the x power. And don't forget a, it's the leading coefficient in all functions, every function that we learned so far. So we always have an a, and the exponential term is b to the x power. B is the base. A is called the initial value. Why we call it initial value? Because if I replace the x by 0, initial means when everything is 0, nothing has started, so x is 0. And you know every number to the 0 power is 1, so we just have left with a. That means the initial value is always a. Base is b, x is the power, x can be any number. We don't have any restriction for replacing numbers for x. That's why we say that the domain of this number, the exponential function, is all real number. Because we can replace any number for x. We can have positive exponent, negative exponent, we can have zero exponent, we can have decimals, we can have fractions, we can have negative, any number. So that's why the domain is all real number. But when we want to find the range has to be found from the graph. But in general form, when you graph an exponential function, you always create a table value. And when you create, for example, you want to graph 2 to the x power. When you create a table value, so you are allowed to replace any number for x, like -1, like 0, 1, 2, 3, any number. If you replace -1, you get 1/2. Replace 0, you will get 1. Replace 1, you get 2. And when you are graphing this one, you will see that the graph never crossed the x-axis. Doesn't have exponent, doesn't have x-intercept. Why? Because if you want to have x-intercept, you have to set the whole function equal to 0. And you try to find the x. You ask yourself, okay, what power of 2 is equal to 0? 2 to what power gives me a 0? Nothing. We cannot find any point. Because any number that you replace for x, it's a power of 2. So 2 to, even if you replace x by 0, 2 to the 0 power is 1. 2 to the first power is 2. Second power is 4. Third power is 8. If you replace negatives, you get 1/2, 1/4, 1/8. You never get a 0. That's why we don't have x-intercept. So the function never crossed the x-axis. So when we are finding the range, we have to consider that from that point going up all the way to infinity. So if a is a positive number, the range starts from 0, the x-axis, and going all the way to infinity. But if a is negative, the graph looks like this. That means it starts from negative infinity and going up all the way to 0. And you can see better when you are graphing functions. We always have a y-intercept. We can replace the x by 0 and find y-intercept for sure. You can see the y-intercept. We may not have x-intercept, but we always have a y-intercept. And you know there is no x-intercept. When we are talking about the exponential function, if b or the base is a number that's greater than 1, that means we have a growth. So we can say that we have exponential growth, and the b is called the growth factor. But if b is a number less than 1, but it still is positive, like 1/2 or 1/3 or 1/4, we have exponential decay. And b is called a decay factor. Let's look at the first example. In first example, we want to we have an exponential function and we want to evaluate it for f of 4 and f of negative 4. Evaluate means find a value. Find a value, find a y value when x is given to you. When it says find f of 4, that means find a y value if x is 4. So you just write the whole function down and replace the x by 4. And you know that you always have to find the exponent based on the PEMDAS. So we have 4 times 3 to the 5th power. What is 3 to the 5th power? What is 3 by multiplied by itself 5 times? It's 243. And if you multiply 4 by 243, you get 972. That's it. If we want to find f of negative 4, this time we want to replace x by negative 4. If I replace x by negative 4 and add these two numbers together, it gives me negative 3. But I don't work with negative numbers. I have to always change them to positive exponent. So how we can change negative exponent to positive exponent? By move it from the numerator to denominator. Okay, so move 3 to the denominator. We keep the base and the power. Just the negative change to positive. Do I have to move 4? No, 4 is a different number. 4 still stays on the top. Only the exponential term must move. Now you need to find 3 to the 3rd power. Multiply 3 by itself 3 times, which is 27. And that is the final answer. So every time they ask you to evaluate, that means whatever number you see inside the parenthesis must be replaced for x. Next example is asking us to find an exponential function. So when every time they ask us to find the exponential function, we remember the general form. Even if it's not given to us. But in this example, it says find an exponential function of this form. We know that because that's the general form of every exponential function that is passing through these 2 points. We know every time a function is passing through a point, that means I am allowed to replace those numbers for x and y of the function. When it says function is passing through 0 and 4, that means I can replace the x by 0 and y by 4. Okay, let's do that. Replace the y by 4, or f of x by 4. And I don't know what is a, I don't know what is b, but I can replace the x by 0. Same for the other point. When it says that the function is passing through 2 and 36, that means I can replace x by 2 and y, or f of x by 36. Okay, let's replace it. Replace f of x by 36. I don't know a, I don't know b, and replace the x by 2. Now I want to use these two equations to find a and b. If you want to write an equation, the only thing you have to find is a and b. That's the goal. Let's look at the first example. In the first example, I see a power of 0. And I know that the power of 0, any number with the power of 0 is always 1. And a times 1 is just a. Okay, which means a is equal to 4. Okay, I found a. I don't need to do anything to find that. So a is 4. After finding a from the first equation, now we just look at the second equation. Since I found a 4, I can replace a by 4 and use this equation to find b. But remember, in this example, I had the power of 0. Power of 0, it makes everything easy. But if you have any other power not 0, you may need to use both of the equations together, divide by each other to cancel the a and find the b, or anything, or just kind of substitution method. to find A and B. Now, using this equation to find B, okay, which means I want to isolate the B. To isolate the B, first I need to get rid of 4. 4 is multiplying by B, so I have to divide both sides by 4. So I have 9, which is equal to B squared. Now it's time to get rid of the power. And to cancel the power, I need to put the square roots on both sides. Okay, power and radical cancel each other, so it gives me only B. And I know that the square root of 9 is 3. But I told you, every time you take the square root, you need to have a plus and minus. That's right. So should I leave a plus and minus here for B in exponential functions? No, because B is always a positive real number. When you are writing exponential function, remember that the B is always a positive number. So you don't need a plus and a minus, just positive real. Okay, now you have both of the A and B. That means you can write your equation. So what is the function? F of x equal to A is 4, B is a 3 with the x. That's the general form of this exponential function. Now let's see how we can graph exponential function. To graph exponential function, again, we need to create a table value. But to create a table value, I need to know what numbers is better or is the best to replace for x. You know that the domain of exponential function is all real numbers. So the domain is all numbers from negative infinity to positive infinity. So you're not restricted to replace numbers. But we don't want big numbers because, you know, especially when we have exponent, bigger number gives you a huge number, which makes it hard to graph. But what do we do to have the best numbers and just, you know, small numbers to graph? First thing that we do, we have to find what number makes the exponent 0. Why? Because this function, it's an exponential function, 2 to the x power, which it has some types of transformation. So the parent function for this function is 2 to the x. And you know that 2 to the x is an exponential function, and if you graph it, since it never gets 0, so it never touches across x-axis. And that's why we call x-axis the horizontal asymptote for this function. But this function that I want to graph has different shifts. And you know, every time x is adding or subtracting by a number, that means we have a horizontal shift. So we have horizontal shift, which means 1 to the right. When you see the function is adding, the whole function is adding or subtracting by a number like positive 3, that means we have a vertical shift, and it tells me that I have to go 3 up. If you have the graph of 2 to the x power, you can just shift the graph 1 to the right, 3 up, and then graph the new function. Otherwise, you need to create a table value. And when you are creating a table value, first you need to know where is the asymptote. The asymptote for all exponential function is x-intercept, unless we have a vertical shift, because only vertical shift this line up or down. Horizontal shift doesn't change this line, because horizontal shift means going to the right or to the left, since horizontal asymptote, it's from negative infinity to positive infinity, so it doesn't change it. But if we have a vertical shift, it will shift it up or down. And you know, in this function, we have a shift by 3. That means all of the points are shifted up by 3. So the horizontal asymptote also must be shifted up by 3. So instead of graphing asymptote on the x-axis, I will shift that 3 up. And I will graph my horizontal asymptote first. Because when I have my horizontal asymptote, it reminds me that I'm not going to cross this line. Okay, now let's go back to finding points to replace for x. I told you, first of all, we need to know where the exponent gets 0. The exponent is x minus 1. And if you set it equal to 0, that means x must be equal to 1. 1 is the point that makes the exponent 0. We put that in the middle of the table, and we always find two x values greater than and two x values less than this number. 2 less than 1 is 0 and negative 1. 2 greater than 1, which is 2 and 3. Let's replace each of them and find the y value. If we replace the x by 1, which is the middle point, we get 1 minus 1, which is a 0. 2 to the 0 power is 1, and 1 plus 3 is 4. If I replace the x by 0, I will get 2 to the 0 minus 1 plus 3. And 0 minus 1 is negative 1. And I know 2 to the negative 1 power means 1/2, because we have to change the move it to denominator to make the power positive. And 1/2 plus 3 means 3.5. 3.5. Let's replace negative 1. If I replace x by negative 1, the exponent would be negative 1 minus 1, which is negative 2. I have 2 to the negative 2 power. 2 to the negative 2 power, again, when the power is negative, I will move it to denominator to make the power positive. And the denominator is 2 to the second power, which is 4. So we have 1/4 plus 3, which is 3 and 4, which is 3.25. This one is 3.5. Now let's replace x by 2. 2 minus 1 is just 1. 2 to the first power is 2, and 2 plus 3 is 5. Replace x by 3. 3 minus 1 is 2. 2 to the second power is 4, and 4 plus 3 is 7. Now it's ready. Let's find the points. So this is 3, 4, 5, 6, 7. So I have 3 and 7, 2 and 5, 1 and 4, 0 and 3, 0 and 3/2, which is the y-intercept, because when you replace x by 0, you get the y-intercept. And the other one is negative 1 and 3/4. It's really hard to graph because it's lower than the previous one. Okay, now you can graph the line equation. It's a curve. And from each side is going to infinity, because domain is all the numbers from negative infinity to positive infinity. Okay, and make sure that you're not crossing or touching the asymptote. Now, if you want to write the equation of the asymptote, the horizontal asymptote, since we have a horizontal lines equation is, since they are crossing y-axis, we always start with the y equal, it's passing through 3, so y equal 3. That's the horizontal asymptote. If you want to show the domain is all real number from negative infinity to positive infinity. You want to find the range. For finding the range, we look at the graph from the bottom to the top. And you know that this graph is not going to cross this line, y equal 3. So it's not going under this line. So we have to start from 3 and going up all the way to infinity. But since 3 is the horizontal asymptote, it still is not included. So we You have to leave it as a parenthesis, which is open. That means 3 is not, but any number greater than 3, it's part of the range. Another example. We want to graph this function. First of all, we need to create a table value. We need to know what number makes the power 0. So the power is x minus 1. And if you set it equal to 0, x must be equal to 1. That's the y-intercept. The point that, So let's replace the x by 1 in the middle of the table, 2 points before 1, 2 points after 1. And we start replacing these numbers for x. If I replace the x by negative 1, negative 1 minus 1, it's negative 2. So now I have 1/2 with the negative 2 power, and I need to find it, but I have to make the power positive first. If I want to if I have 1/2 with the negative 2 power, that means 1 has a negative 2 power, and 2 also has a negative 2. And to make a power positive, you need to flip it. You have to switch from numerator to denominator or denominator to numerator. So I'm going to switch these two to make the powers positive. Now 2 to the second power is 4, 1 to the second power is 1, and so is 4. So this is 4. And 4 times 4 is 16. Let's replace x by 0. 0 minus 1 is negative 1. And 1/2 with the negative 1 power is just 2. And 4 times 2 is 8. Replace x by 1. 1 minus 1 is a 0. And you know that 1/2 with the 0 power, any number with a 0 power is just 1. And 1 times 4 is 4. Replace the x by 2. 2 minus 1 is just 1. And we have 1/2 with the first power, which is 1/2. And if I multiply 4 by 1/2, cancel 2 by 4, and so we get 2. Or 4 over 2, which is 2. Replace the x by 3. 3 minus 1 is 2. And when we say 1/2 with the second power, means 1 with the second power and 2 with the second power, which is 1/4. And 4 times 1/4 is just 1. Okay, let's find the points. But we always have to find the horizontal asymptote first. I told you the horizontal asymptote is always x-axis unless we have a vertical shift. Do we have a vertical shift in this function? Do you see if the whole function is adding or subtracting by a number? I see x is adding or subtracting, but that doesn't, this is a horizontal shift. Do we have any vertical shift? No, because there is no number here which is adding or subtracting by the function. So if there is no vertical shift, the horizontal asymptote is still x-axis. So I will graph a dotted line to remind me not going through or touching this line. And then try to find the points. Negative 1 and 16 is a big number. I'm going to skip that point. 0 and 8. 1 and 4. 2 and 2. 3 and 1. Okay, so we graph Connect the points going up and also getting close to this line. If you look at this graph, you see that from left to right, the function is going down. That means the function is decreasing. But if you look at the last example, you see from left to right, the function is going up. That means it's increasing. And what is the difference that this one is increasing, the other one is decreasing? It's just the base. The base is 2, means we have a increasing function, we have a growth. But if base is 1/2, which is less than 1, we have a decreasing function or decay. So that's why we explain here that every time b is greater than 1, like 2 or 3, we have a growth, we have exponential growth. And if it's less than 1, like 1/2, we have exponential decay. And we can use this exponential growth and decay in application problem. Okay? And you know that in every exponential function, as we said, a is always the initial value, the starting value of the function, b is the growth factor. If it's greater than 1, decay factor if it's less than 1. Okay? Let's look at an example. It says a small town has a population of 100 people. The population grows by 5% each year. Write a function that represents this situation. When it says a small town has a population of 100 people, that's the initial value, which is A. When it says grows by 5% each year, that means this is a growth rate. Okay? But you know, B is the growth factor, not the growth rate. There is a difference between the growth rate and the growth factor. Growth rate means the percentage of increase. That's a 5%, but you know that we never work with percent in the problem. We always have to change it to decimal. So instead of having 5%, we just put 0.05. But when we talk about the growth factor, which is B, that means we are adding that rate by 1, because that growth is after the first year. So we had 100% of the first year, and it's increasing by 5%. So we have 100 and 100% plus another 5%, which is 1 plus R. And 1 plus 5% is 1.05. Now, if I want to write the equation, I say f of x, it's equal to a is 100, b is 1.05 with the x power. So this is the equation. Okay? Because b is the growth factor. Rate is different. Rate is just a percentage. Let's look at another example. It says the population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. Okay. The population was 1.25 billion, the initial, the beginning, so it's A. Annual growth rate is 1.2%. 1.2%, that's the growth rate. So rate is 1.2%, but we have to change it to decimal. I know it's decimal, but still we have to change the percentage. Every time you can use the percentage key on your calculator, or you can just, you know, when you want to change the percent to decimal, we always move the decimal points 2 digits back and just leave it here. And if any number is missing, so you see we have a spot here with no number, you just leave a 0. So the answer is 0.012. That is the growth rate. But if you want to find the B, which is the growth factor, you say 1 plus R, or 1 plus 0.012. which is 1.012. And if you write the equation, you will see that the equation is look like this. A times b to the t power. T is the time. T is the number of years since 2013, as the problem mentioned. And A is the initial population, or the population in 2013. Now it says interpret A in the context of this problem. A is 1.25 billion, which is the initial population, or population in 2013. Interpret B in the context of this problem. B is 1.012, which is the growth factor. Okay, which it means that the population is increasing by 1.2% each year. Now it says, to the nearest thousand, what will the population of India be in 2031? Okay, you want to find the population. That means P of t. So let's write the equation first. Because to solve application problem, we always use equations. If equation is given to us, so feel free to use it. Otherwise, find the equation first. In this equation, we have a t and we have a p of t. T is the number of years. P of t is the population. Okay. We want to find the population. So we want to find P of t. So P of t is not given to us. If P of t is not given, you want to find it. That means T must be given to you, the time. When it says in 2031, and we know T is the number of years after 2013, we have to say, okay, 2031 is how many years after 2013? So 2031 minus 2013, it's how many years? So the answer is 18. So you have to replace the t by 18. Now we just type this one, the whole in the calculator to find the answer. So we say 1.012 to the power of 18, and then multiply it by 1.25. And the answer is 1.549, because it's to the nearest thousand. And that's it, 3 digits after the points. So the population in 2031 is 1.549 billion.